In about the mid-1800s, some people started to notice that electricity and magnetism were linked in a very particular way. If you took a coil of wire and hooked it up to an ammeter, and then put a magnet by the coil, nothing happened. But if you waggled that magnet back and forth, a current showed up in the circuit. And the reciprocal situation worked too. By that I mean if you left the magnet alone and waggled the loop, you'd get a current in the circuit from that too. As long as the coil and the magnet were moving with respect to each other, you got a current. We call that an induced current, and we call this phenomenon electromagnetic induction. At first it was pretty magical looking, and to this day it's still kind of amazing. But before too long, people managed to wrap this behavior up in a formal law known as Faraday's Law, which is one of the 4 Maxwell equations. The law shows up in a bunch of different forms. And you can get from any of these to any other using some mathematical operations. They're equivalent. Note that Faraday's Law is the first Maxwell equation that's explicitly time-dependent. And it's also the first one that explicitly links electric and magnetic phenomena. For now, let's just worry about 2 of the forms. This form is the simplest looking, and is the one you're most likely to use in any kind of practice. It says that if you have some loop, and the amount of magnetic flux through that loop is changing with respect to time, then there'll be an induced EMF, or voltage, around the perimeter of that loop. And if the loop is conducting, that voltage will be able to drive a current. Now you can get a changing flux lots of different ways. You might have a magnetic field that's changing with respect to time, as would happen if you had a nearby magnet and moved it around. That changes the flux on account of the changing magnetic field near the loop. Alternatively, you might have a flexible loop of wire that's changing size, like a loop that has a slip knot so that you can pull it closed. And that changes the flux by changing the area of the loop. And the most practical approach of all is to take a loop, a source of magnetic field, and rotate the one with respect to the other. The latter is how electrical generators usually work to this day. Recapping that, Faraday's Law says that any time you have a changing magnetic flux through a loop, you induce an EMF in that loop. This particular form of Faraday's Law is pretty agnostic about how that EMF comes about. This form is more explicit. It's the same law, but with the gory bit showing. Over here on the right, we have an integral of B over some area. That's a magnetic flux, and then we hit it with a time derivative. So that's our negative d flux dt term. Over here on the left, we actually have 2 terms. If I split them out, they might start to look a bit more familiar. This term is the integral of E along some path. That's what a voltage looks like. What's special about it, though, is that it's an integral along a closed loop. Back in statics, the integral of E around a closed loop is always 0. Faraday's Law shows us that changing magnetic fluxes can lead to E fields that are non-conservative. These E fields are fields that have curl, and they can act continuously around a loop, so that if you're a charge going around in a complete circuit, you can end up with more energy than you started with. These curly E fields come about whenever you have a changing magnetic field, which, as you may recall, is one of the ways that you can have a changing magnetic flux. I'll say it again. Curly E fields come from time-varying B fields, something important enough that I'll put a bunny on it for emphasis. Now, the other term in Faraday's Law is the integral of a V cross B thing, where the V represents the motion of the loop itself. Remember, if you have a loop and a magnet, and the loop is moving but the magnet isn't, you still get a changing flux and therefore an induced EMF. But you don't have a time-varying B field, so you don't induce a non-conservative E field. But the fact that you're pushing a loop of wire full of electrons through a magnetic field can result in a magnetic force that pushes the electrons around. So this form of Faraday's law explicitly shows the two different ways that you can get an EMF. Having a time-varying B field leads to a curly E field that can drive a current, and having a moving loop can lead to a motional EMF that can also drive a current. I'll close out with a little story from the history of physics. When Faraday first came up with this stuff, he'd go around with little magnets and coils and do demos for the public. The public thought it was a neat circus trick, and not much else. One time, as the story goes, this woman sees the show and says, "Mr. Faraday, of what use are your discoveries?" And Faraday says, "Madam, of what use is a baby?" It turned out to actually be a pretty apt metaphor, since within a couple of decades, people had figured out how to use these circus tricks to make electrical generators and power grids that could light up cities. The moral of the story, then, is to not be too quick to dismiss some phenomenon that no one has an immediate use for. It just might be the thing that some clever engineer figures out how to use to turn the lights on.